Okay. So let's start a couple of steps from last week, so we can jump smoothly into this third part. So I will be showing you the last part here, just for this example that was crashing last time. So, and I will reintroduce all these concepts. So this is one entire example of how you solve this original problem, that's taking some here. So the serial version of that was super short. It was basically computing a vector here and here cosinus square and sinus square, and after subtracting those two vectors. And here we have the CUDA version of that. So that's what we will be entering. So I will be discussing a little bit this one. And after we will re-enter and refreshing that with some pictures, some plots. So how you do that. So basically in CUDA, you have four things that you need to be aware of. One is how you allocate memory on the device, because on a GPU, on your GPU has a separate memory. So the memory where you are playing, for example, if you're using the GPUs for gaming, all the textures, basically that, and all the geometry information is stored on those 2, 4, whatever gigabytes of memory you have for the graphic card. That memory is not accessible directly by the CPU. So the GPU can see it. And the reverse is also true. The GPU cannot access directly the memory in RAM. So those two memories are separate. So that's why you have to do different allocations for whatever you want to put in RAM and the memory that you want to put inside the GPU. So so here is how you allocate with this function that is well, belongs to the standard library in C, malloc, and there is one very similar that is called CUDA malloc for allocating arrays or pointers on the GPU. So that's one thing. Second thing is that, again, as those memories are separate, you need functions to copy memory back and forth between the host and the device, and from the device to the host. Here we are not copying from the host to the device because we are filling all that information directly inside the GPU. But there is one function here. Okay, all the function is always this one, memcpi. But you can decide on which direction you want to make the copy, from the host to the device or from the device to the host. That's the second thing. Third thing is the kernel. So here you have the function that you want to use inside the GPU. Somewhere here. So think about this as, for this case, whatever you want to put inside the loop that will be spanning on many threads. So you create an integer that you will identify for every single element in your array. And here you are doing all the operations. So here is where all this heavy computation in principle will take place in this kernel. So this is the third thing. And the last part here is how you call those functions. here. Again, we will review this when we enter this specifically in the chapter for today. So notice that in CUDA, we have things like this. When you have things like this, that immediately breaks entirely what the C language specification declares. So this code here is no longer C, pure C. And only can be compiled with a CUDA compiler. So this is one of the reasons because why this is no longer C code, and also the existence of this global here. There are several identifiers for this. Global is one of them. Global is because we will be calling functions from the host to be running on the device. There is another identifier here, like a flag for functions that are called by the device for the device, and functions that are to be working entirely on the host, so CPU only things. And you can even mix some of them, so you can have a host plus device, and CUDA will generate double code. The routines for the CPU and the routines for the device, for the GPU. So those are the main elements here. So right now it's a little bit confusing, but we will enter in this with pictures, with some stuff that we clarify all that. And also, well, we will discuss in a minute what is the meaning of this, the blocks and grids. So how CUDA manage the thousands of threads that you create when you are parallelizing this code with many, many threads. And so the reverse of that, so we have here functions to move data from the device to the host. And here, this is the allocation for whatever you have allocated for the CPU, for the memory, for the RAM, and the equivalent deallocation functions for the GPU. So that's exactly what I'm describing here. You can go and read this. And so let me try to get into this code to demonstrate how you compile this. Let's see if I can jump into Thorny and do it on Thorny before we start moving into something else. So I will be logging into a Spruce, well, just because I jumped from Spruce. But okay. So I will be sharing now my screen on the terminal. It will be this one. Okay. So here I am on Thorny Flat, on the head node of Thorny Flat. And remember that here I copy data from this place. So here in share software mini workshops, we have this folder. So all the material that I will be creating or discussing here, it will be here on Thorny. So let's go and work with this. So let me go to Scratch, and I have my copy here of all that code. So what I will be doing is to ask for an interactive session. It's equal 1, ppm, let's say 8, GPUs equal, and I forgot the name of that. So it's this one. So this is how you request one interactive session, with one node, a course, one GPU on this queue. So you notice that you get relatively easy one node here. I actually don't know how Phil is right now. Well, how Phil it is. GPU, no one. And here, the GPU weak. Okay, there are 25. I don't know how easy it will become to get in on Thorny for interactive jobs. Anyway, so let's go here, scratch GPU for the computing. So the first thing is to load the module for CUDA, CUDA 11. And again, this code, let's review this on XP CUDA. So this code is no longer C, it's not longer pure C code. Again, we have a couple of things here like this that break the language specification. So, and also this global blah, blah, blah. This C will not be able to compile that. You can try, it will complain basically, saying that code is, that format is not recognized. Well, even if you rename that, it will not. So you compile this code with this NVCC, that means NVIDIA CUDA compiler. So the compiler recognizes the code. It will basically take all that, remove, understand those special words that depart from the C language. It will probably remove them, operate with that, removing a little bit the code and exposing to the compiler, to the C compiler, the correct C code, and it will do other manipulations to produce the code that will run on the GPU. So here I have, and I execute this code, and okay, this is an old version. When I have a bug and I forgot to change it. Well, we can, it's just a small bug, I think, that I create. Let me see if I can capture that. What I did here when I was copying this. Let me see if I remember what it was. I don't remember. Something trivial. Anyway, I will not waste my time here. Let's jump into the material for today. So what we will be understanding actually. It will be, is this one? Oh, no, it's not this one. It will be this one. This one. Okay. Okay, so CUDA is relatively new. It was introduced in 2006. Before that, before CUDA exists, people start programming GPUs actually for doing scientific computing. but they have to talk in the terms of a graphics processor. So when you want to multiply matrices, you have to reformat all that in terms of rotations, applying a texture or applying. So you probably need to talk in the language of a game to do the math that you want to do. And NVIDIA changed all that when they standardize and create CUDA. So that stands for Compute Unified Device Architecture. And the basic, or the great idea with CUDA is that it creates an abstraction where you don't pay too much attention on exactly all those CUDA cores or all that internal. We will explain all that because it's important for performance understanding. But you basically imagine that you have a black box device and you just generate thousands of threads, hundreds of thousands of threads if you want, and they will execute on that machine. So the system will figure it out which threads will go, how to go together, and how to move. But you are not constrained to think about how many threads you have as you are on a CPU. On a CPU, you have, okay, how many cores do I have? Okay, so I need to explicitly, when I am executing, knowing that I will not be using more than 20 cores. And so I will be MPIs if you are combining with MPI. Okay, so MPI number of processes, 20 or 40, whatever. Here now, you just launched thousands, hundreds of thousands. Even if the actual number of CUDA cores is probably 1,000, 4,000, is 4,000 around 4,000 on the latest GPU cards that we have, the RTX 6000. But you don't pay attention to that much. That will flow, and all that will go and compute. So that's one nice thing of this. As CUDA have been progressing over the years with CUDA version 2, version 3, 4, one of the things that they allowed is to first, originally they arranged the threads in groups, like in planes, because it comes from this idea of a graphic card, where what you have is textures that are basically two-dimensional objects, and all those planes and all that. So it's very, very two-dimensional. And now they allowed a scheme where you can arrange threads in three-dimensional hierarchies. We will see those three-dimensional hierarchies in a minute. And even you can not use that and be happy with just one-dimensional hierarchies for the threading. That's another important thing for CUDA. And the fact that you have this global memory, the GPU memory, there are several memories on the device, but when we talk about the GPU memory or the global memory, as in calling CUDA, is a big memory that is part of the GPU. It's inside the GPU, inside the GPU card. Even if they have several levels of cache and the CUDA cores are arranged in a specific fashion. So there are several things here. When you are creating a kernel, all the different threads are executing the same code. So that is what we call, in computer science, they call single program, multiple data. So it doesn't mean that the code needs to execute exactly the same instruction at the same time. That is a different concept. But at least they are executing the same code, the same kernel, all whatever the code is supposed to be doing, all are doing the same, the same code. So How you differentiate that? For each thread, they have a couple of identifiers that together will identify uniquely which thread are you talking to, and that will redirect the code into dealing with a specific location in memory, different position for an array, all that. So that's what is. So here we're making the representation of a thread with this like a line, a threading line or something, and all those threads here, and basically follow those lines in the code. They receive a different thread ID or something like that, we will see, and they will eventually diverge and they will be computing different stuff, but they move that way. Now, the threads are arranged in a hierarchy. The big level, B level, is what is called a grid. A grid is a collection of blocks. Here we have n blocks from 0 to n minus 1. And each block is a collection of threads. So here we have like 3, 6, 7, 8 threads here. So then the number of threads on each block is the same for all the blocks that belongs to the same grid. All those have access to the memory and they can coordinate the work together. We will see that probably not today, but for the next one. How that organization works, and that organization is the key element for performance. So keep that in mind. You can create an range of blocks. They could be an one-dimensional list of blocks with one-dimensional list of threads on each block, or in the most general case, you can create a three-dimensional array of blocks where each block is a three-dimensional array of threads. And they have some limits for the number of threads in a block. That part depends on the GPU, so on the specific card. So some of them, they have limits of 1024 core threads on a single block. And I think then the latest version of the most recent cards, they have expanded that. I don't remember the value. Okay, so that is important. That is where this start becoming confusion at first. That's why I'm going very, very slowly, because this is critical for understanding later performance, debugging, and all that stuff. So again, arrange on a grid. A grid is many blocks, and each block is many threads. So now, here we have another example. Let's say we have a two-dimensional grid. So this grid is a two-dimensional arrange of blocks. So we have the block 0, 0, 1, 0, 2, 1, 2, 0, 0, 1, 1, 1, 2, 1. So we have two numbers here that identify this block. Now, here I have a zoom into one of those blocks, the block 1, 1. The block 1, 1 have an array of 4 times 2 times 2 threads, so that three-dimensional range of threads. So here we have 16 threads in this block arranged in 3 dimensions. And here we have a grid in 2 dimensions for the blocks. So this grid in total will be 6 times 16, the total number of threads in this. So the code will process all that, and eventually later you can change and eventually call it the same kernel, the same function, with a different grid. And the arrangement of threads will be entirely different. And the GPU will take decisions how to arrange those threads and how you process all those threads inside the GPU. So This is an abstraction. Again, we are not thinking at this level of understanding, we are not thinking in terms of CUDA codes or who is doing what or what is my limitation. I'm supposed to overload the system with more threads than the actual number of cores in such a way that we have always something to do on the GPU. Something is moving inside. So now, from the hardware perspective, inside the GPU is arranged in what is called an streaming multiprocessor. So an streaming multiprocessor is this kind of a structure, this kind of idealize something like that. In hardware, it will probably look very different. But they basically have the collection of instructions and they have schedulers, warp scheduler. Warp is a collection of threads that go together. Right now, it's 32 threads that constitute a warp. So even if you have here a block here with a certain number of threads, they will pack together in sets of 32 to create a warp, and those will execute a single instruction, multiple data. So all those threads that are in packages of 32, they go together, they execute the same at the same time. So that is not super relevant. Right now, it will be relevant for performance considerations, but just for you to know. So we have in a streaming multiprocessor, so that's why they call it here SM. Inside, they have a number of GPU cores here and another electronics here for managing the scheduling of all the threads that you have here. And imagine that this streaming multiprocessor has some restriction, or it has some restriction on the number of threads. The scheduler will put work based on the data availability that we have for processing, trying to maximize what you can do with the actual cores here. Okay, so yes, in general, those are 32. So 32 is a magic number in CUDA. You should try always to arrange everything in multiples of 32 or something for the number of threads, just because they are arranged, packed in that number. So that's the recommendation. So try always to go in multiples of 32. Okay. So thread identity. Again, all those threads are running the same code, but they are identified differently for a set of numbers. So there is one number here that identify, which is actually could be three numbers here. So this is a set of at most three numbers. It could be just one. That identify the block. And this one is again a set of at most three numbers. They identify the thread in that block. So with the thread IDX, with the three numbers in the thread IDX and the three numbers in the block IDX, we can pinpoint exactly an individual thread on the entire collection of threads for that grid. And that's what we do when you are running this for vectors, for matrices, for arrangements of all kinds. Typically, if you have one-dimensional grid, so it's a list of blocks, you will have just one direction. So the X value for that block identifier and one direction. So one value here, the X that identify the thread in that list. So it will be just one-dimensional list of blocks, and each block one-dimensional list of threads. That is the perfect case when you are dealing with vectors, for example, because with this equation basically, so dx, the bx is the block dimension times the identifier for the block plus the identifier for the thread. This equation will give you a number that go and crosses all possible values for a vector. So that's the natural way of doing it for a vector. For a two-dimensional grid, of course, that changes, and probably is much better if you create your grid with two-dimensional blocks and eventually each block with a two-dimensional set of threads. So that in that case, you have an equation for identifying the location in the x direction, another equation for identifying the location in the y direction, and with that you can pinpoint an array exactly with an x, y value. So, and same thing, more complex for three-dimensional grids for cases where you demand such thing. So that's the most that you can do. Beyond that, you need to arrange. If you are working in 4 dimensions, you need to figure it out how you will arrange the threads, probably just in 1 dimension, and manage yourself the concept of the 4 or more dimensions for the system. Now, and again, we will go back in a specific example of the code below how that works in practice. So memory hierarchy. Again, when we talk about the memory in the GPU, when you see here, let me jump here and share this back again. And this one. So here, this code. So here, when you see here with this command, no. I know what I did. I understand now what I did. What I did here. Oh, okay. No, I got it. Okay. Okay. I made a mistake before, so it was not. It was inside a machine with GPUs, but I was not allowed to use the GPU. So that's why I was getting errors until that. So first, the machine has a certain amount of memory, and that is the value that you can get here when you execute this command to inspect the amount of memory on the device. Actually, I probably can do something like this to give an idea in the case. Let me see. Yeah. Okay. So I'm basically requesting the internal. So in this case, I have 3 GPUs, 3 cards in this machine in particular, and each of them have 24 gigabytes of RAM. One important thing is that this is just what is called the global memory for the GPU. 24 gigabytes of RAM here, 24 gigabytes of RAM here, and 24 gigabytes of RAM here. The memory on each card is independent for that card. So they will not be able to see the memory from a different card. And also the GPU is not able to see directly the memory on the GPU, except for something in the most recent versions of CUDA with some link memory, but we will not be discussing that. So this PIC 6000 has 24 gigabytes of RAM. Notice one important thing is that RAM memory, the GPU memory, is considerably more precious, valuable than the RAM on the CPU. So that's one thing. And another thing is that processing single precision floating point number is at least double, and usually more than double, faster than double precision numbers. So that's why GPUs were very, very good or are heavily utilized in cases where you don't need double precision, like processing, in many cases, neural networks. So all those neural networks, you don't really need double precision in many cases. So you are happy with that. And in classical molecular dynamics, again, you don't need all that extra precision. So memory fits much better when you have arrays in single precision. That double precision, you are saving half the space, and you are performing double or more with that. So this is what we call the memory, the global memory. So now I jump here into this, back again. And we have this global memory that we show here with this blue square. That is just for one device, this 24 gigabytes for one device. And now we design kernels that work with the memory in the work on top of this global memory. So we are able to manipulate data in there, creating kernels with different numbers of threads. And those threads arrange in different arrangements of grids. So there is a limit for the number of threads. There is a limit for the number of threads in a block. In most cases today, you can consider this, a block could have up to 1,000, and you are covering a wide range of GPU cards today. Again, those are specific for each GPU, so you need to be aware of that. Again, each thread, each block here, they have access to their own memory inside the GPU, inside this arrangement here, inside. So they have a portion of memory that is devoted, like cache, they have all the registers for there, and they are individualized for the block. And at the very end, we have the thread, and there is a memory associated for that individual thread. So during the existence of the thread, that memory is allocated and discarded after that. You don't have control on that memory. That is just for you to know that that thing exists. You basically only control the global memory. So you arrange, you create arrays, you create matrices and vectors, and you allocate that memory on the global memory. And from that beyond is the GPU machinery who will move that data. It's pretty much the same what happens on the CPU. You have control on what you allocate on the RAM memory, but you don't have control. You don't have direct control on the cache. So you don't manipulate which elements go into a cache. You try to make things in such a way that you use and reuse as much as you can the different levels of cache, and that's why you arrange the operations in a certain way instead of another. But you don't have that control in most cases. Okay, so now let's go and review all this in practice with code. So again, the four elements, the four pillars for CUDA, for programming in CUDA. Memory allocation, how you move data in and out, device and host, the creation of kernels, and how you call those kernels, and how you manage it, right? So the blocks and grids and all that. So we will be basically discussing all this with the small pieces of code, so we remove all the noise around. So that's why we will not see here complete codes. So the first part is the memory allocation. This routine and this routine. This one, well, first, here I am allocating a pointer. That pointer is in the RAM. But this is pointing with this. So a pointer is basically a piece of paper. Imagine a piece of paper where you have written the location in memory where you can find something. So, an address, okay, an address. In this address, I can go and find this. Well, this piece of paper, this portion of an information is in RAM. But it's pointing, when you make the allocation, it's pointing to a location in memory inside the GPU. For making that clear, usually the people put this D underscore, whatever. This is a good idea to make that differentiation clear. You put this D underscore. So I'm here storing I will be here storing the location in memory for something that is inside the GPU. So it's in another place, not the CPU, not the RAM. And here I am counting how many bytes I need to arrange for storing n numbers, n floating point numbers. So n times the size of a float, it's typically 4 bytes. So here I'm making this allocation. And here I am using this. You can take this as a recipe, basically. But what it's doing is basically removing all that and getting just the pointer naked. So removing all the specification about the floating point, all that, because it will go to a different device. So you don't need that. And you just need the location of memory where you will put that information here. And at the very end, you deallocate that memory. At the very end, or when you need to do, you don't need it anymore, and you can just free that memory. One example, for example, could be, okay, you have, imagine if you are thinking about classical molecular dynamics, and you want a vector to contain all the positions of your atoms in the space. So you know how many atoms you have, you make the allocation 3 times the number of atoms that you have, and you will store in there the location. So you put all that in the GPU, you will manipulate all that inside the GPU. And if for some reason, whatever you are doing, you need to change that, you can free that memory and allocate again and increase the number of atoms. You are discarding and creating with a different number, whatever, you can do that. You free, you allocate and deallocate. That's one thing. So, okay, this is the first pillar. Second, moving data is just one function. It's just this one. Here is a little bit counterintuitive, but here you decide which is the destination or what you want to copy into. So you want to copy here from the host to the device, this location into this. This one is an array on RAM where you will store in all those elements. And you declare here the size, and this goes from the host to the device. I actually think here's uppercase. Here, I think I have a typo. And here from the device to host. So you are copying back. You want to print, you want to see the data, storing the data somewhere else on a file, you need to copy all that data back to arrays on RAM so you can manipulate that, all that information with the CPU. So that's how the GPU works. That's basically the extra effort on working with GPUs. Now, here comes what is the tricky part at the beginning, is figuring out how to manipulate this hierarchy of threads with a GPU. First, how you declare kernels. Kernel, well, and I think again, I have a typo here. This should be void here. Here in the middle, I have a typo. You should put here void and the function where. So here, an identifier, an integer, for example, for an array, for a vector, an integer here with this equation, I can pinpoint one individual element on the array. So imagine that we have an array, a linear array of blocks, and each block, for example, have 10 elements. So the dimension here is 10 blocks. So the first one here will be the block number 0. The block identifier will be 0. So this one will be 0. And all those threads there will be 0 to n, the number of threads that I have created here. After that follows the first block here. So the next block, 10. So 11 to 19, or 10 to 19, 20 to 29, if we are working in blocks of 10. So this equation will give you exactly that, a consecutive number of integers that will cover the entire array. And after that, you manipulate that and you do whatever you need to do with that array. So in this particular case, what I'm doing is basically filling this array to identify that the block ID with the number beyond 1000 and the trait identifier with just the number. So when you look at those values together, you can see, and it's a good experience to see how that actually works. Two identifiers collectively give you one integer for working with that. So now we have this example here, and a small example, and the next, the exercise will be to join all this data, this small data, for making this to work. Basically looking at this example and start playing a little bit. So here, this example contains more than I will be asking you for the example. So here I have this this kernel here. So this is what I forgot to put in previously, this void. So here I have my arguments for the vector, for one vector, another vector. And here I am filling the values of y with a given number times the value on the vector x plus the value on the vector y. So basically an increment by x. And again, usually this number should be larger, or equal or larger than the value of the size of the array, size of the vector. So that's why you put this conditional. Otherwise, you will be trying to write values beyond the length of the vector. Makes no sense. Okay, so now inside here, what you are doing is allocating the values for the arrays that are in RAM. So this one is in RAM. And here a few pointers. So over here I have a few pointers. Those belong to the host, will be arrays that I have on the host. Those will contain locations for memory that belong to the device. So here, this is the allocation for the host. Here is the allocation for the device. same, basically the same, or the same length for both both cases. So now, in this case, for example, I am filling the values here on with 1 for all the elements here, 2 for all the elements in Y, and I am copy these two values from the host to the device. All those from the host, and this is what it is counterintuitive, because this is the destination actually. This is where everything will be written, and this is where everything comes from. So typically in Unix, everything is source destination, but this is the other way around. So here's the destination, here's where you will be writing the values, and here is the origin of those values from the RAM. And here is what I'm calling the function. In this particular case, I am hard coding the number of threads per block. So I'm deciding, okay, I want 256 threads on every single block. All blocks will contain this number of threads. So whatever is left is knowing how many blocks we need to fill the vector with that. This is one trick. This is one way of doing it. Another way is with ceiling, with the function ceiling. I don't know computationally if that makes too much difference, choosing one over another. I have seen both in exercises and examples. So basically you take the value, you add 1 minus just to be sure that when you make the division, you cover sufficiently good all the values in the array. So that will be creating this expression here. Inside here, you will be creating one grid with one-dimensional list of blocks, with one-dimensional list of threads on each block. So it will go concatenating threads on that. And the size, well, it was not decided here. Oh yeah, this trick. So it's what, 1 million? This trick here is, it's a little bit obscure. It's basically moving 20 spaces to the right. So it will be 2 to 20 minus 1. So this should be 1 million, I think. Let me see. Yeah, a little bit more than 1 million. Okay, so yeah, 1 million elements, 1,048,000 elements. So that's what you are doing here with this trick. So all those, so basically you are creating all those, or that million of threads. Even if the GPU itself will not have 1 million cores, they don't have 1 million cores in that, but the whole idea on the GPU is don't care about it. Don't care about the huge amount of threads that you are creating, just create those threads. And the GPU, if the GPU is small, it's a desktop game for gamers, those small GPUs that cost less than $1,000 are able to do that, are arranging that. But if you have those expensive GPUs that has 4,000 cores, they are also able to do it. So don't pay too much attention on oversaturate, oversubscribing the number of threads. Something that you don't want to do on a CPU by any means, because you will be losing cache, memory. It will be a mess if you put 1 million threads, CPU threads to run on the CPU. So notice the difference when you are working with CPUs versus GPUs. And so once you have all that, you are copying back all the memory from the GPU to the CPU, to the RAM, to the memory that the CPU can see. So you are copying this number of elements from device to host, from the device to the host. The location for the device is here. You will be copying all that here. Once it's here, you can start printing all the values if you want, or just printing here. Basically, they are computing the error that in this example, and at the very end to free this the memory on the device and free the memory on the CPU. So for the RAM, basically. So this is an entire program. So now the exercise, it will be kind of using this for making something even simpler. So you can start patching, copying and paste this. Basically, the idea is to create an array where you store the values like this, where you store something like this for all the elements of the array. 1000 times the block identifier plus the tree, the identifier for the thread. That is something. Okay. Okay, Joe. I got it in message. It's okay. And so that's the example. That's the exercise. So you should be able to complete the exercise with those small pieces of code, copying and pasting, and using small pieces of this code. Actually, less than this. So you actually need to remove things from this code. So let me see. Let's see if I can go here and let me see. I will be jumping here. Here. Okay. So okay. So this is the original code, the example code. And the exercise is basically pruning this code to do something much simpler and compile it, and eventually you will start getting the idea of all those 4 pillars for GPUs. So it's not that hard. Programming in CUDA is not that. Once you understand all those 4 things, is really not that hard. What is hard is doing well. What is hard is getting good performance with that. Typically, the first implementation offers the worst performance. So we will see that in the next lesson. So for this introduction, so understanding the performance, how you select the grid, how you select if you will be doing the blocks 2-dimensional or 3-dimensional or just 1-dimensional, or the blocks, arrange the blocks for the grid in 2 dimensions or 3 dimensions, and the size of that. Should I make the blocks fatter with more threads on each block and making less number of blocks, or make the blocks thinner, less number of threads, but more blocks? So, and there are reasons why you want to choose one or another. And part of that is GPU dependent, so depends on each individual GPU. And part of that is not so dependent. So So let's see, I have here the code. Module is what I have here, module load, parallel CUDA 11. And so in this small exercise, again, all that I'm doing is just computing this function. So this is the kernel. This is the kernel, and I'm here, I'm making just a little bit of each pillar. So the kernel, the allocations, the movement of memory, and how you call the function here, how do you manage the threads and in the grid blocks, all that. So that you start playing with this, and we will be ready for the next lesson next week. So I compiled that, and this actually doesn't show much. Let me see. Yeah. And now I can compile this. That fails last time. My DAXP CUDA. Okay. So now it's okay. So now it's showing the right values. It was before not having enabled the GPU and will start failing because it never put anything on the GPU. So that's what we have, and now we have a few minutes to explore that. And I think I will be sharing that. Okay, sharing back the screen here. This one, I think. Yes. And when we, well, now, Nick, okay. So I right now, the most consistent guys are you two in this lesson. So do you want me to redirect this more into classical molecular dynamics? It could be nice.
Sure, if you want to.
Because I mean, that's your area. That's your area.
It is, yes.
So you're probably not super interested in and Alfredo. So Alfredo was not today. So missing ballots are not counted here. So it will be with you. If you want to direct this.
Do you want me to keep the recording going or just stop it here?
You can stop it here. You can stop it here.